We have Leo Rivera from Meter Group. Leo will be talking about what is the true volume of influence for soil moisture sensors, evaluating methods for quantifying volume of influence from soil moisture sensors.
All right. Thanks, Nathan. And Victoria, thanks for setting that up. Just mentioning volume of influence. I kind of thought this talk was going to stand out and not really blend in well with the rest of the conversations, but I think it's actually going to fit in pretty nicely. But today, I want to talk about volume of influence of sensors, the methods that we use to evaluate that and what we see, and ultimately, what's the right way to do it? And so that's kind of the question I'm posing to the community, but let's dive into it. So we all know that soil moisture can be highly spatially variable, especially due to heterogeneity of soil that was just discussed. We see differences in wetting front patterns, all these things that create differences in water content, even across a very small scale. And of course, we're just taking these point measurements and using them to try and represent much larger areas of soil moisture. And so that can be challenging, even when we're trying to relate data across profile. Tyson gave a really great talk on earlier, about sensor placement and how that represents different depths. I think that's a really important thing to think about. And as sensor manufacturers, one of our goals is to try and increase that measurement volume of sensors so we are better quantifying some of that variability and better averaging soil moistures across scale. And, how do we ensure that the characterization of the sensor measurement volume truly represents what we see in the field? And I haven't really seen any standards for this. And I think it's something that we need to think about. But let's kind of keep diving into sensing volume for soil moisture sensors, specifically dielectric-based soil moisture sensors. There are a lot of factors that influence the electromagnetic field and the sensing volume of dielectric-based soil moisture sensors. You have the sensor geometry, the size of the needles, things like that. The operating frequency of the sensor also impacts what that looks like. And I don't have this on here, but there are also factors in soil that impact what that volume actually looks like. And again, that's not something that we do a really good job of characterizing and trying to quantify. So how do we really quantify what this sensing volume is? And so that's the goal of what I'm going to try and discuss today and go over some of these different methods. So we wanted to evaluate some of these different methods we use for measuring the volume of influence from sensors and try and come up with what's the correct approach. And we also wanted to see how these different methods of evaluating sensor volume compare and what we see in that. And so in this talk, I'm referencing 3 different methods that we typically use for looking at sensing volume of sensors. The most common one that we use is we have the sensor in air and we move it towards a water interface. Another method we're going to look at is in a container of water, and as we move that sensor towards an air interface to see what that response looks like. And the last method that we're going to look at is actually in moist soil. I believe the soil is around 25% water content. I'll go into that. And as we shave those layers down, how that sensing response changes. And one last point I'm going to hit on is sampling volume versus volume of influence, because I think those are 2 very different things. Sampling volume is actually where the bulk of the measurement is being made for the sensor, and the volume of influence is how far you can put things within the area of the sensor that actually impact the measurement. And both of those are actually 2 hard things to quantify, but we'll dive into that. Okay, so like I said, the first method that we were going to talk about was the air to water interface test. And the way this works is you have a sensor. Typically, the way we like to do it is we place the sensor on the table and we secure the sensor to the table. That way we're not influencing the sensor at all. And we have a thin-walled acrylic container filled with water. And what you do is you move that thin-walled acrylic container closer to the sensor in all of its different orientations and see what the response looks like as you're moving it closer to to the sensor. And here you can see some examples of those graphs on the bottom. The first graph on the left is one of the sides of the sensor. So it's standing up and we're approaching the side of the sensor. And you can see as we get closer, you can start to see what that response looks like. This is going to be really low because in air, we're measuring a dielectric permittivity of about 1. And so we're really looking to see when that starts to increase. And you can see that there. And then you can see the same response approaching the needle side of the sensor. And these measurements are referenced to the middle of the sensor body. And that's kind of where we reference all our measurements. So you'll see that that stops at about 5 centimeters because that's the length of the sensor needles. So that's what this measurement looks like. This is what we used to determine our current measurement volumes for sensors. And so that's what we've used for a long time. Another common approach is essentially the opposite of what we just did. We have the sensor placed in a large container of water. This container needs to be large enough to actually contain the full volume of influence from the sensor. Here we have a large fish tank. I can't remember how many gallons this was. 50 gallons, something like that. Yeah. And what we did is we set up an apparatus on the tank that allows us to move the sensor in multiple angles and orientations and move it around the container. And what we're doing is just measuring again, just like with the air interface, we're measuring as we move it or just like the previous method, as we're measuring as we move the sensor towards the air interface, we're measuring that change in sensor response and looking what that looks like. And then we use the criteria to evaluate what our volume is there. And you can again see similar examples to the one before, and you can see our same measurement from side 1 and approaching the needles as we move towards the edge of the tank. Of course, this is the opposite. Now we're looking for a decrease in the dielectric permittivity response from the sensor. And then this is our last method that we're going to compare. We've done some comparisons to some other approaches as well, but I'm not bringing those up because those were methods that we got from Andres Patrigani. He did some his student did some great work in that area, and I'm excited to see some of the things that they present on that because they got some really interesting results. But with this method, what we're doing is we're taking essentially a molded block of wet soil. We used Palouse silt loam for this test and wet it to about 26% volumetric water content. And what you do is you mold the block of soil and then you place the sensor in the block of soil. In this case, we have the sensor just pushed in from the surface. So we don't have the full body submerged in the soil, just because it was easier to do that for the packing. But that's something that we can look at to see if it really matters if we have the body of the sensor in the soil or not. I don't think it makes that much of a difference. And what we're doing here in this case is we're actually shaving that block of soil down from each side. And so what we'll do is we'll shave from one side, look at that sensor response, and then we'll remold the soil and then do the same thing from the opposite side. That way we're trying to minimize some of the influences of what that looks like. And again, you can see what that response looks like. Let's see. Yeah, so from the same angles again, you can see what it looks like shaving off from either side and from the needle side, and you can see what that looks like in terms of dielectric permittivity. And I might have the water content wrong in my head, so because I'm looking, this is dielectric permittivity. But I think the important question is, what did those values actually look like for those 3 different methods? And what we found is that we had a wide range of results from the 3 different methods. And so this is from, these values are from the Teros 15 sensor, which is one of the sensors that people are able to play with outside. But you can see that the air to water interface method produced a volume of influence of about 226 cubic centimeters. The wet soil method produced a volume of influence of 432 cubic centimeters, and the water to air interface method, so in the tank of water, produced a really large volume of influence of about 936 cubic centimeters. And so some of the things that are really interesting, one, I always expected that when we placed a sensor in soil that volume was actually smaller than what we saw in our air tests. And it turns out we were wrong. And this is the criteria that we used for setting these measurements is a 95% signal response, to try and limit some of the noise that we would see from that. So we see big differences just with the presence of water. So that's the really, I think, interesting thing to note is that as we add water to the system, the volume actually gets bigger. And I think one of the questions that I want to continue to explore is in soil, as we change water content, how does that volume of influence change? And I think that's some of those things that you'll actually see come out of that work that's being done by Andres Padragani and his student. And they found some really interesting results from that. But the other thing that this really makes me question is, what is the right way to measure the volume of influence? And so that's something that I hope we can discuss more and come up with a more standardized approach, especially to simplify when you're looking at different manufacturers of sensors. You understand that those measurements can compare across the industry. And then one last piece I wanted to hit on, and hopefully I won't take too much time on this, but we're talking about volume of influence right now, which is the volume that you see responses from the sensor. But we all know that for most dielectric sensors, the bulk of the measurement that is impacted is near the needles of the sensor. And we see that here. These are some models from a numerical electromagnetic computation tool from Lawrence Berkeley National Lab, I believe. And so it's a really neat tool because we can use it to create different sensor designs and evaluate what that electromagnetic field actually looks like. And here you can see a 3-pin design with your center needle as the active needle and the two outside needles as your grounding needle for that this type of sensor. And you see kind of a 3D image of what that electromagnetic field actually looks like. But also you can see the contour lines of where that sensor is actually, how far that electromagnetic field is extending. And we've done quite a bit of work looking at different needle spacings to see how that impacts the sensor sampling volume. And so this has been really neat because it's a really powerful tool to help us as we're working on sensor designs to try and improve what that sampling volume looks like. But you can see here as you change your inner needle spacing that you actually wind up with very different looking electromagnetic fields. And the wider space of the needles, it actually brings that field closer into the needles, and you actually don't extend out in between the needle gaps as well with that. And you can, too far. You can see what that looks like with similar contour lines. And you can see in this graph on the left that you see more contour lines in between that black outer contour line, which is our 10 volts per meter kind of criteria where the bulk of the response is in that area. And you see that essentially the collapse of the contour lines means that that field's collapsing down a little bit. So to conclude, we see that different methods of measuring volume of influence produce a wide range of results. I really think we need to standardize the approaches that we use to make things more comparable, and ultimately the goal should be to better represent what we expect to see in soil. And a thing that we still need to better understand and better quantify is sampling volume versus volume of influence. And again, like I said, we want to better understand how soil moisture changes impact the volume of influence in soil. And so with that, I'm going to conclude and say thank you.
That's an interesting concept. We use the same methods that you do at Acclima. We do the water to air, the air to water measurements. But we've noticed that the main factor that influences the sampling volume is the conductivity of the medium. The attenuation of the electromagnetic field is a big factor. And if there's conductivity present, then the field goes way down. So even more than with moisture content. So that's another factor that needs to be taken into consideration. It doesn't do any good to have a sensor with a high sampling volume if you put it into conductive soils.
Yeah, that's a great point, and that's also something we've discussed and have been playing around with and doing some of these tests in different conductivity solutions to really see how that changes. But yeah, that's a great point.
I got a question. Tyson had some discussion yesterday about depths and where should we, what depth should we be sampling at? And obviously at the deeper ones, this information is not applicable, but at the shallower ones, in your mind, how does that discussion, how is the information you've got here, how can that give us some insight in how to look at the shallower space?
Yeah, I mean, I think there's a couple things. One, it's important to know that because if you're trying to do shallow measurements and you have a sensor that field might actually extend into the air, you need to understand that when trying to do those shallow measurements. But also in understanding, like, really, if we're looking at 5 to 10 centimeters or 10 to 20 centimeters, if we have a sensor that's encompassing a pretty broad range of that, how much spacing do we really need to quantify that soil moisture in the shallow layers?
Oh,
For the shallow sensors, if it's possible, there is some air influence from above. Is that something we would do as a calibration, like take that information to calibrate? And then given that you tested the influence on the base or the head of that sensor, what do you think about the fact when we stick it in the pit wall and that's the intact soil, and then we have a changed structure, bulk density when we refill that back hole? How might that change in soil influence the measurement? And then rocks, did you test the influence of rocks?
Nathan, you're really going to get your steps in today. Okay, I'm trying to remember all the questions. That first one, I do think if you know that your sensors, that measurement interface is going to be exposed to air, it is something that you can calibrate for. I mean, we've dealt with that in other medias where you're calibrating to a much smaller block, so it can be done. It depends. I mean, we've done it so for example, in small growing blocks like that are maybe not more than like 4 centimeters in diameter. And so we've had to deal with calibrations for things like that. And so it's feasible. I think in most cases it probably wouldn't be, but in some cases it might. I mean, and that's the other piece is we're seeing is as the water content increases, that field actually might extend. And I think that's something that we need to better understand when we're thinking about those shallow measurements. And then your second question, the last question was rocks. No, we haven't done anything with rocks. And I think that was a common discussion point in the soil specific calibration workshop earlier. And that is a good piece to try and better understand. Did I cover everything? Oh yes, this body of the sensor. I think for the most part, that area is pretty minimal. Like we know that some sensors have some sensitivity off the head of the sensor, but it's pretty minimal compared to everything else. So I don't think it really makes that much of an impact on the actual accuracy of the sensor.
thank you, Leo. I just want to say, like, I think getting the manufacturers talking about how their stuff works is a really important thing for us. I mean, especially some of us that are coming from the Met side. We got maybe a good handle on how those other sensors work. And in general, I mean, soil sensors can kind of be sort of a black box. And I think, thanks a lot, Leo. I think this kind of insight is really helpful for us.